Let us see motivation for developing object-oriented programming languages. Alan Kay coined this term object-oriented programming. It began with Alan Kay and Smalltalk. Prior to Smalltalk, Simula was also there, but Smalltalk is considered as first real object-oriented programming language. Kay was motivated to create object-oriented programming because of several influences. He found that in traditional procedural programming, as program gets larger, it would be difficult to manage these programs. They are more error prone and more difficult to debug and revise. System design with these kind of languages more difficult to change and less stable in operation. He wanted to create programming architecture that could scale software from very small to very large without losing its flexibility nor its ability. To understand it clearly, let us see what are the problems with early languages. First and early second generation languages like Fortran and COBOL have flat physical structure. Applications in these languages primarily consist of global data and subprograms. Here, flat structure means data and subprograms are organized linearly without any hierarchy or clear separation. In these languages, subprograms are the basic building blocks of applications. This flat physical structure contributes to the lack of logical separation between different kinds of data. Errors in one part of the program can have widespread effect due to global data exposure to all subprograms. Same data can be used by all these subprograms. Maintaining the integrity of the original design becomes very challenging here. Lack of modularity leads to difficulties in maintaining clarity, reliability, and overall system integrity. Modifications and maintenance over time become very challenging. In late second and early third generation programming languages largely follows the patterns established by earlier generation languages. In these languages, subprograms were seen as abstraction mechanisms. This led to the development of procedural abstraction. There are several advantages with this generation languages over early generation languages. Despite of all these advantages, maintaining the integrity of original design when modifying larger systems remain challenging. Because here also this flat structure is maintained, there is no clear separation between data. So these languages are also not efficient to build larger systems. Let us see the problem with the global data, which is main problem of first and second generation languages. In procedural languages like C, data does not have owner. This leads to the problem of difficulty in maintaining the data integrity. Let us see the small code here. Int t equal to 85 and this print statement. Here t is the data which is publicly accessible by the code around it. Means any function can read it and can also modify it. This is the shared data. Let's assume as t can be accessed by these three functions. If something goes wrong with this data, it is very difficult to identify which of these three functions misbehaved to create the bug. Late third generation programming languages starts with Fortran 2. Introduce separately compiled modules. These modules served as a containers for grouping data, allowing different parts of a program to be developed independently by larger development teams. These modules supported some form of modular structure but lacked semantic consistency among module interfaces, leading to potential runtime errors, posing challenges for program reliability and debugging. Developers across different teams make assumptions about parameter types and data structure within the modules, leading to inconsistencies across modules. For example, this subprogram or module expects certain type of parameter, let's say integer. Another module incorrectly called with different parameters like double. All these modules share common data, assuming certain properties and structure, but other modules might violate these assumptions, leading to potential runtime errors and difficult to maintain program correctness. Object and object-oriented programming languages represents a significant advancement in managing complexity compared to earlier procedural languages. Procedural languages does not have ability to describe abstract objects. Consider a banking system implemented in procedural languages like C. We might have series of procedures for handling various banking operations such as deposit, withdrawal, and money transfer. However, managing customer accounts, transactions, and other banking entities become very difficult due to lack of direct support for abstract objects. This led to the emergence of data-driven design methods. In object-oriented languages, the fundamental building blocks are classes and objects instead of subprograms. Unlike procedural languages, object-oriented programming languages have little or no global data. Instead, data and its related methods combined within a class. This kind of encapsulation of data and methods provides scalable mechanism for managing complexity in large systems through hierarchical layers of abstraction. This kind of architecture used for moderate sized applications using object-oriented programming languages. For larger systems, classes, objects, modules serves as a fundamental building blocks for abstraction. However, they might insufficient on their own for very large complex systems. Object model scales up to handle this complexity by organizing layers of abstractions. For example, if we take large applications like Amazon, e-commerce, for lower level abstractions, we have classes such as user, product, and orders. These classes organized into modules like user management. Let's say this is user management, product catalog, and order processing, and checkout process. Within checkout process, there are meaningful collection of objects including shopping cart, payment gateway. Within the shopping cart, another set of cooperative abstractions like item, quantity, price. This is the topology for very large applications. In object-oriented programming, programs are organized as a cooperative collection of objects, each object representing an instance of a class. With classes, we can form hierarchy through inheritance relationships. Object-oriented programming consists of four major elements: abstraction, encapsulation, inheritance, and polymorphism. To design large-scale applications, we need languages which support object-oriented programming principles like abstraction, encapsulation, inheritance, and polymorphism. Languages which support all of these principles called as object-oriented programming languages. Object-oriented programming languages offers a framework for modular and hierarchical abstraction. This model is crucial for effectively managing complexity in software development. In next class we will see some introduction to Java, some of the most prominent features of Java, and how to write Java programs and how to compile the Java programs in the next class.